start. Welcome everybody to the webinar of today. The speaker of today is Esteban Ferrer, and he's going to talk about new avenues in high-order fluid dynamics. As usual, I introduce the speaker and then I leave him the floor. So Esteban Ferrer is a professor of applied mathematics at the School of Aeronautics, ETCIAE UPM. He obtained his PhD by the University of Oxford in UK and has 20 years of industrial and academic experience in developing numerical techniques for fluid problems. He works actively with industry and coordinates the two EU projects. His main interests include high-order methods for fluid dynamics, turbulence modeling, machine learning, aeroacoustics for aeroacoustics and wind energy. For aeronautics and wind energy. He has written more than 90 journal and conference papers on these topics, and it's with great pleasure that I introduce Esteban Ferrer for the seminar of today. So Esteban, I stopped sharing my screen and you can start sharing yours.
Okay, thank you very much.
Yeah, we see your screen.
You can see it.
Perfect.
Right, so thank you very much for the invitation. It's with great pleasure that I'll introduce some of our solvers and also some of the new ideas we're incorporating into our high-order solvers. So, well, these are my contacts, some acknowledgement to my collaborators, and also acknowledgement to the students. This has been going for a few years, and also the current funding, of course. So in our department, we develop numerical methods, in particular for incompressible and compressible flows, and they're basically based on high-order discretizations and discontinuous Galerkin techniques. We also do flow stability and sensitivity studies based with the idea of doing flow control, but I'm not talking about this part today. And we apply both high-order codes and flow control techniques to aeronautical applications, wind and tidal turbines, and multiphase flows. So the summary of the talk is as follows: a brief introduction of the interest of using high-order methods, and in particular discontinuous Galerkin. I will also present our solver, and then some of the features we're adding to our solver. So these are listed here: moving meshes, multiphase, and turbulence. And finally, I will talk about some acceleration techniques. So this is local adaptation, local mesh adaptation, and then fusing high-order methods with neural networks or even reinforcement learning. Just a glimpse on some things we are doing these days. Right, so I'll start with the introduction. So for those who are not familiar with high-order methods, they require a grid. So we need an edge mesh that we call. So this is these triangles here at the bottom. And then in low-order methods, we represent the numerical solution inside each triangle by a piecewise constant value, or in finite elements, a piecewise linear variation inside the element, similar to what we have here. Now, in high-order methods, what we do is we allow the polynomial to be of arbitrary degree inside each of the triangles. So here we use quadratic polynomials, cubic polynomials inside each of the triangles. And this allows us to capture better the numerical solution in each triangle. So there's two ways that we can to improve the numerical solution when we use high-order methods. One is to increase the number of triangles. So this is subdividing these triangles here. This is the classic method also in low-order methods, but we also have the possibility of changing the polynomial order inside each other. So the change of the polynomial we call p-refinement, and the change in the grid we call h-refinement. So this is increasing the number of triangles. And then one wonders why one will do one or the other if they both achieve similar targets. And the answer, I think, it's in this plot. We can see for a Poisson equation, this is an elliptic problem. And we can check the numerical error here in this axis against the degrees of freedom on the x-axis. And here we have used 4 different meshes, from 32 triangles to 128 triangles with different colors. In the boxes, you can see the polynomial order used to get the converged solution. So if we fix the polynomial to order 2, the only way to increase the accuracy is to increase the number of triangles. And then we have to move along these lines. This is what we call edge refinement. And as we can see, the error decreases rather slowly. However, if we use a very coarse mesh, this is the red one, for example, with 32 triangles, and we increase the polynomial order following this line, what we see is that the error decreases very fast, much faster. That's what we call exponential convergence, and that's a much efficient way to decrease the error. So fix a coarse mesh and increase the polynomial order in each element. Right, so what this means is basically if we want to reach a particular level of accuracy, say 10 to the minus 7, we will require fewer degrees of freedom, so a smaller size for our matrices to be solved, if we use a higher order polynomial on a coarse mesh than if we use a lower order polynomial and edge refinement, and then we have to go outside the screen. So the idea, that's the potential of higher order methods. We need fewer degrees of freedom to obtain high accuracy. So this is, of course, it's a quite theoretical problem, just a Poisson equation. When we see in terms of the Navier-Stokes equations and in a more realistic application, and we compare higher order solvers here with P5 with a very coarse mesh, and we compare it to a commercial code Fluent, for example, second order, what we observe is that the numerical errors act on the wake, and we quickly lose the structures after this cylinder, like this airfoil. However, with the higher order method, we see that we keep the structures well shaped for a long time, and this is because we have very low numerical errors in the DG solution, in the higher order solution. We see this also when we go to turbulent flow fields. So if we compare a DNS from this paper to a lower order code with RANS turbulence modeling, we see that we lose most of the structures, the high frequency structures. We keep the shape more or less of this outer detached flow, but we lose everything. However, when we go to the higher order setting, even in a very, very coarse mesh, H mesh with polynomial order 5, we see that we capture most of the high frequency content. Of course, not everything because the mesh is very coarse, but we do capture much more richness in the flow field than with the standard low order RANS methods. Right, so we have the higher order methods pretty well developed. We can do laminar flows, turbulent flows, well, a lot of things. I'll show you a few more later. And then the framework, the code we are developing now, it's called Horses 3D, and it's based on DGSEM. It's a particular version of discontinuous Galerkin, a nodal version of discontinuous Galerkin, which is quite well known for its efficiency. The bases are by Kopriva in his book, and we were collaborating with him at the beginning of the project. So a few things we have developed since these starting points was we have now compressible and incompressible solvers. We use entropy or energy conserving schemes for stability. So this helps. Well, I'll talk a bit later about that. We use p-adaption. So this is increasing the locally in each element the polynomial order. You can choose different polynomial orders in different elements. We have implicit, explicit time marching, we have LES, and we have RANS. I'll show some results later. And then also we have what we call multiphysics, and this includes multiphase, immerse boundary methods, shocks, etc. So the solver is available on GitHub, so you can go and download it and have a look and play around. And the main features are included in this paper, which is still under review, but you can find it in arXiv. Right, so here's the main. Well, some of the things I'm going to be talking about today. Right, so in terms of efficiency, what we observe is that when we run the code in 1,000 processors, now we have also included 2,000 processors very recently, but I don't have the graph. What we observe is that we get very nice scalability, almost ideal scalability when we go to high polynomial order. So when we increase the polynomial order, we are really making use of all the machinery embedded into the solver, and then we get very good scaling. But this is combining MPI with OpenMP. So this is interesting because what we then see in a more realistic case, so this is the aeroacoustics on an airfoil. You see here the acoustics emanating from the trailing edge. What we and this case has turbulence models, has everything. We have the generation of acoustics and also the propagation of acoustics. When we measure the some pressure level at a particular point here, far from the airfoil, we observe this kind of graph with respect to the frequency, the some pressure level. What we see is that we get some p-convergence as we increase the polynomial order. We get this exponential convergence. So the error decreases very fast when we increase the polynomial. And this is interesting, particularly because we're not losing these theoretical approximation advantages that we saw in the elliptic problem. So this is Navier-Stokes with turbulence models, etc. In addition, the more interesting perhaps is that we decrease the error exponentially, as I just showed, but the cost of the computations only increase linearly. So this can be seen if we plot the CPU cost against degrees of freedom. So we fix the H mesh. So this is fixing the number of triangles or quadrilaterals in this case, hexahedra, in fact. And we increase the polynomial order from 2 to 5. And we see that the increase, it's linear. It's not exponential. So the error decreases exponentially when we increase the polynomial. However, the cost only increases linearly. And this is due to the particular version of the discontinuous Galerkin we use, the parallelization strategy, and everything. Right, so that was the solver. I'll show you now some features that we are adding to the solver. Right, so I'll start with moving meshes, sliding meshes, etc. So in the past, I've worked a lot with hanging nodes and sliding meshes. So this is when the inner mesh rotates and the outer mesh is static, and you can see that the contours go through the interface without any spurious oscillations whatsoever, so they don't care that there's an interface. And this is exactly what you want from a sliding mesh technique. Now, this method it's good. I like it quite a lot. I did it during my PhD. However, it's a bit costly. It's a bit costly because you have to compute this connectivity between nodes and elements all the time. So during these last, I would say, years, we've started focusing on mesh-free methods. So mesh-free methods, they're also called immense boundary methods, right? And in immense boundary methods, what we can do is we can have a Cartesian mesh, so there's no need for complicated meshes. And then we penalize in some particular nodes, this is higher order nodes in the mesh, to represent the solid boundaries and the geometries. Right, so the implementation is fairly easy and allows us for complex geometries and moving geometries to be done very easily, again, with no meshing. And if you are a CFD practitioner, you like not meshing, right? I've been doing this for a long time and I don't like meshing. Right, so if we see some results, we see quite good results when we start moving objects in this background mesh. And in particular, what's perhaps more interesting is that when we move these objects, we can check the effect of the polynomial in the numerical solution. And we see this, we don't lose the spectral convergence behavior when we increase the polynomial. So as we increase the polynomial, we get fast to these converge solutions. That means that, I mean, these kind of methods have been sometimes criticized because you lose some accuracy near the boundaries, etc. But what we observe is that this loss of accuracy, it's very limited to the near cells near the body, and hence overall you get a quite accurate flow field. You don't really lose the advantage of using polynomial, high order polynomial. So these methods are suitable for high order settings. But you can see the details in these two papers, and we have a few more on immense boundaries with high order methods. If we push a bit further this type of methods, we can think of a wind turbine, right? So the wind turbine will have a fixed structure and then rotating blades, right? And I would like to emphasize that here we only need the STL file that you can extract from the CAD geometry, right? So if you have the STL file, we can use a very simple Cartesian kind of mesh, and we can have the results. So the method, the solver, will penalize. So these are the points that will be penalized in the mesh that will represent the moving geometry. If we look a little bit at what we get, in this case, we get this kind of flow fields. Of course, there's no bodies really represented here. It's all mesh, right? But And in this particular case, we've used polynomial of the 3 for the wake and polynomial of the 1 far away from the wake, such that we can get better accuracy in the near field of the wind turbine. Now I can always superimpose into the flow field the original cut, although it's not necessary. So we're taking care of that, and we see that in fact the flow field represents what should be represented. In particular, what we see is that we get the physics that we would expect from a wind turbine. So we get the tip vortex, we get the leading edge acceleration, we get tower wake and tower shadows, etc. Right? So these days we are able to represent wind turbines and rotating machinery with different levels of accuracy. So we can use actuator disks. So this is very simple representation, just like a porous jump. We can use actuator lines. So this is, we only represent forces for the blades and then we rotate that. We can do immersed boundaries and we can do sliding meshes. So we have a bunch of different accuracies to represent rotating things, rotating machinery. Right, if we look at the multiphase stuff, so there's a bunch of methods to do multiphase. I'm not covering that at all today. The well-knowns are the volume of fluid, for example, but we focus on phase field models. So phase field models are good and suitable for high-order methods because they represent the interface between the two immiscible fluids. So this can be air and water, for example, as a smooth function, something similar to a hyperbolic tangent. And this is a smooth interface. And in high-order methods, we like smooth interfaces because we avoid Gibbs phenomena, etc., when you have very sharp changes. So to control the position and the behavior of this interface, what we do, we need to solve some additional equations. This is the Canhillier equation. And we couple the Navier-Stokes to the Canhillier equations to have the whole thing. Right, so if we see some typical flow fields for multiphase, we can see that we can represent the classic flow fields. And one of the things we've been doing recently is allowing p-refinement. So this is increasing the polynomial order only at the interface between the two fluids. So this will allow us to save some computational cost and capture the interface between the two fluids quite well. Right, so you have here a bunch of papers that you can check. Right, so one of the things that is interesting in high-order methods, not high-order methods really, it's CFD, it's that you can improve the stability of your numerical solutions by using entropy stable or energy stable discretizations. I'll explain very briefly what that means because it's very easy to understand. So if we think in the continuous setting, so this is the Navier-Stokes equation, for example, right? One can show that you can derive from the Navier-Stokes equation a kinetic energy equation or an entropy equation, and the Navier-Stokes equation are fitting the energy equation. So they fulfill also in the continuous setting the energy equation or the entropy equation. So this is true for the continuous setting, but it's not necessarily true when you discretize the Navier-Stokes equation. So if we discretize the Navier-Stokes equation, in our case using DG, but any other method, the discrete form of the Navier-Stokes equation doesn't necessarily conserve energy, right? Kinetic energy, for example. So if you check, then the kinetic energy is not conserved. What this means is that there's no mechanism for the discrete equations to not blow up because of an arbitrary increase in energy, for example. However, if you take your discretized equations and you make sure that they also fulfill a kinetic energy equation or an entropy equation, that any of those, you are bounding this energy and you're making sure that the energy cannot grow exponentially because it's balanced, right? And this is what we do. So it doesn't mean you need to solve additional equations. You don't solve additional equations. You just go in the paper when you derive your discretization, you check that your discretization also fulfills the kinetic energy equation on the paper, and then you solve the Navier-Stokes equation. So there's no additional cost. It's just a check. If you do so there's some particular technicalities here. So you have to use Gauss-Lobato nodes, etc. There's a few details that I'm not going into. But if you do so, what you observe is this kind of behavior. So if you have a very well-resolved flow field, so this is where the interface it's very smooth, for example, you see that the standard DG and the one with the energy or entropy stable form behave very similarly. So they're both stable and you reach the final solution. However, when you start increasing the under resolution at the interface, so this is we are not fine enough in the mesh to solve every single flow feature, right? So we have some under resolution. What we see is that the standard form blows up, blows up. However, the split forms, so the ones with the energy conservation, do not blow up, and you get a stable solution. And this we see for various flow fields, in particular when we get very under-resolved interfaces, as in this case. So this is on the resolution idea, and these energy stable, entropy stable methods are also very suitable for under-resolved turbulence, right? So this is the same idea. We don't capture all the single structures. We have some aliasing errors, and these split forms help us to alleviate this problem and help us to get stable solutions when sometimes otherwise they're unstable. Right, so I'm talking turbulence. Let's go into that. So we work in RANS, Reynolds average Navier-Stokes. In particular, we have used the Spada-Talmash-Neck turbulence model. And what we see is that when we check our convergence for the CD, for example, for the drag, for this NASA workshop case, what we see is that we very rapidly get to the right solution when we increase the polynomial. So this is the same idea. Increasing the polynomial gets you very fast in terms of degrees of freedom to the right solution, right? And when we compare our solver to classic finite volume solvers, we see that we require fewer degrees of freedom than with typical finite volume solvers. So this is exactly the idea of high-order methods. Right, another example could be this aircraft that we've solved with our solver and also with the commercial code of Ntoukas. And we see that very quickly when we use polynomial order 3 or 2, we get to the right solution. Whilst with the finite volume solver of Ntoukas, you need quite a few more degrees of freedom. Right. So one small detail is when we run RANS, we want to reach a steady state solution. And to reach a steady state solution, you want a fast numerical iterative solver to get to the steady state solution. So this is what we do. We use a fast multigrid, right, following this kind of V-cycle structure or W cycle structure, whatever you want to call it. And we use some semi-implicit smoothers as well. So if we use the multigrid with local time stepping, for example, what we see is that we need 10 to the 5 degrees of freedom to converge to the steady state all these meshes, right? And this is with a variety of polynomial orders. So the higher the polynomial, the longer it takes to converge. But when we switch to the semi-implicit smoother, so this is also the called Burke scheme, what we see is that we can bring down and that's wall clock, okay? The wall clock time to 500, 5,000 of 6,000. So from 10 to the 5 to the thousands, right? So there's a big improvement in changing to this kind of smoothers. Right, we do RANS, also we do LES, and in terms of LES, we've used implicit LES. So this is allowing the numerics to take care of the subgrid scaling. And when we do this with these energy or entropy stable formulations, this is the same idea for multiphase, but now for turbulent, for one-phase flows. What we see is that we get reasonably accurate solutions when we compare to experiments. So this is Horses 3D, this is our solver, the red dots, and we see that both lift and drag for these airfoils looks quite reasonable. Right, we very recently, so this is last week, we have been comparing our solver for a Formula 1 simplified front wing, where we're comparing our solver to Imperial College Nectar. So this is incompressible for Nectar. This is ours, and this is a relatively highly computationally expensive simulation. and we see relatively a good comparison in terms of CP and in terms of other quantities that I'm not showing here. This is work in progress, of course. Finally, we have some collaborations with Barcelona Supercomputing, where we are looking at a bit more carefully, on the difference between implicit and explicit LES. When we need one, when we need the other one, do we need both at the same time? So we are looking into that. So we have various turbulence models implemented, Riemann, Weyl, Smagorinsky, etc. We have various energy entropy stable methods also implemented, and we're trying to see these combinations when they are necessary or not. Right, so okay. Very briefly, we also work on shock capturing techniques. I'm just showing here some examples, but I'm not really going to talk about that. So that should be a movie. So we're combining shocks with LES, etc. So with RANS, this is RANS in fact. So we have a bunch of different methods to capture shocks. We are also developing this. Right, so I'm coming towards the last part of my talk, where I'm going to be presenting some new stuff, new ideas. Right. So the first one is local adaptation. So how can we concentrate the high polynomials only in the regions that are necessary? So we know higher polynomials bring us very quickly to the right solution, but maybe we can concentrate the degrees of freedom in the regions that are more likely to necessitate these degrees of freedom. So a particular case is a boundary layer where we have in the normal direction we require a high polynomial order, whilst in the streamwise direction we need a low polynomial order. So we allow for anisotropic polynomial refinement in different directions. So how do we select the right polynomial in the right place? I'll explain that for a steady case, because I think it's easy to understand. We have extensions to unsteady cases as well. You can ask me about that. So if we consider the Navier-Stokes equations and we consider steady state, so this is 0, we get this thing here. Now, we can use the truncation error definition. So this was not given by us. The truncation error, it's the Navier-Stokes operator discretized at a particular discrete level n, where you have plugged the exact solution, right? The exact solution in this operator. And that gives you the truncation error. There's another term here, which is the exact operator and with the exact solution. But this, in our case, the steady case is 0, so we don't have to consider this. So the truncation error, then, it's just the Navier-Stokes operator where you have to plug the exact solution. Now, of course, we never know the exact solution. However, what we can do is approximate the exact solution with a finer polynomial. We can use a polynomial p, which is going to be finer than this discretization n. So we can plug the u at a finer level p in this operator, and we get an estimation of our truncation error. So this is the basic idea. What we will do is we will run a solution here. This is the p solution, right? We will extract the up, so the solution here, and we will plug in all these operators, which are coarser, right? That's Rn, that's p-1, p-2, p-3, then it's p-, and we will plug the exact solution in all those, right? We don't need to solve an additional problem for each of these levels. We only plug the exact solution into the operator and get a result. Okay, so there's no necessity for solving the problem. So the only one that we have to solve is this one. With this, we know that the truncation error decreases exponentially. So it follows this idea that when we increase the polynomial, everything decreases very fast. And hence, what we can do is do an extrapolation. So fit a linear curve, okay, through all these points, and then extrapolate to the accuracy that we require. This gives us the polynomial order that we need to reach a certain level of accuracy. So this extrapolation idea we have done a few times. That can be done in multiple directions. You can do in different to get the polynomial that you need in different directions. And this is how we can select the polynomials. So this is what we did in this case. We've done that in more complicated cases. And what we see is that if you use an homogeneous polynomial, the error decreases. This is true. It decreases fast. It's true, but you require a lot of degrees of freedom to make it decrease because you're wasting a lot of degrees of freedom. However, if you do the local adaptation, an isotropic local adaptation, you get to this line where the error decreases very fast for fewer degrees of freedom. Right. So when we were writing these papers, we were often criticized by the reviewers saying, but why don't you use adjoints? So people like adjoints are very nice. I'll explain you the reasoning of why sometimes it's maybe better to use what we do. So in adjoints, what you typically have to set to the method, it's an error in a particular functional. So you select the leaf, for example, and you say, okay, I don't want an error in leaf that is larger than 10%. Right? And with this, the adjoint method will give you a mesh that fulfills this criteria, right? It will give you a new mesh where the error is below 10% error. Okay, so what we were able to show in this paper in 2016, after the reviewer asked us for it, is that if we use the truncation error, so this is this guy here, the proof is very simple. In fact, it looks complicated here, but it's simple. If we use the truncation error, when we decrease the truncation error, this guy, we are in fact controlling any error in any functional. So when we decrease the error, we are decreasing the error in lift, but also the error in drag, also the error in any functional that you can imagine. Adjoints are not like this. Adjoints, you select an error in the lift, you will get the mesh that gives you that particular error in the lift, but there's no guarantees that the drag will follow this decreasing error. The drag or any other functionals could even increase. They don't necessarily have to decrease. So with the truncation error, you control any functional. So you might need more degrees of freedom to do so, but you are controlling everything. So we like this idea, right? And very recently in this paper from actually this year, it's a short note, so it's easy to read. What we were able to do is using this inequality, you can in fact link the truncation error threshold. So this is the value that we need to do our adaptation to particular functional errors. So now with this new methodology we put forward, we can say, okay, I want an error of 10% in lift, right, for the lift. And then I will compute based on these guys here that are dividing the truncation error that will give me this 10%. So we've closed this open question of how the truncation error relates to adjoints and in particular to lift, drag, functionals, etc. So you might think, oh yeah, but you need to compute what the hell is this? You need to compute the inverse of the Jacobian, something like that. Well, we put forward in this paper very efficient ways of computing these guys, right? So this is only related to the singular value of the Jacobian, etc. That's we can do that efficiently. Right. Another thing we've done in the past is all this idea of having a solution and different operators of different levels, you know, and going from one level to the next is reminiscent to multigrid. So we exploited that in the past where we were using multigrid and a bunch of fast multigrid type of method. And because we are already computing the different grid levels in the multigrid cycle, we can every so often use all this information to do the adaptation. Because we already have all these meshes, we can embed that in an automatic way where we every so often we do the adaptation with the information we already have for the multigrid. And if we do so, we get much faster computations. In particular, when we do this red curve is adaptation plus the multigrid. Right. Very recently, we have gone in another direction. So we have started playing with clustering techniques to get the regions in the flow field that need to be adapted. So we can use some clustering, some particular invariants of the strain tensor, and we get these regions. We get the regions where we should use a high polynomial order and the regions where we should use a low polynomial. If we check the difference when we use clustering with doing homogeneous pre-refinement, and sorry, and this is a turbulence, this is Reynolds 3900 for a cylinder, so this is turbulent flow field. We observe that we get very similar solutions in terms of Struhal number, drag, etc. Right, I'm almost there. Have a couple more things to show you. So this is a new idea that we've been exploring. So we have already a paper published in the one-dimensional burgers version of this problem, and we have another one which is on the Rubio on the three-dimensional Navier-Stokes with turbulence. And I'll show you some results from the last one. The idea is very simple. It's when we use high-order methods, if we use a low-order method, low-order polynomial, the time step that we can use in our simulations, it can be very large, right? Whilst if we use a high-order polynomial, the time step in our simulations has to be very small. And this relates to the CFL condition where space and time are linked. And then if you have a very fine resolution, you need a fine time step. So the idea was, okay, is there any way that we can march in time with a low-order discretization with very long time steps, but every so often, when we need the solution, so every time step, for example, we can correct the lower the solution to obtain the filter higher the solution. So correct the low accuracy with the high accuracy. Right, so it's not difficult to see the low order evolution will follow this. This is only done for explicit Euler, but we have that for Runge-Kutta schemes. So this is the low order evolution of the variable. This is the high order evolution of the filter variable. And of course, they give different solutions. But what we propose is, okay, let's rethink on the low order solution and correct it with the neural network to get the high order accuracy. Okay, so what we will do is in each of our low order nodes, so this is still high order setting, right? In each of our Gauss nodes, we will correct the solution to get the high order solution. We will include a forcing term in our equations that allows us to get the high order solution. Okay, so where is this correcting term coming from? Well, of course, from a neural network, right? And you will say, so what do we do? So now I'll show you the example with the Taylor Green and Reynolds 1600. So what we will do, of course, if you have to train your solution for the whole time, that doesn't make any sense because you have to run a high order polynomial, you will run a low order polynomial, and then you have to correct all the time. So there's no gains whatsoever in terms of cost. Now, the idea is it possible to train only in a small window, such as this time, get these source terms that correct our solution to get the high order accuracy only for a short window, and then allow the method to continue and correct the solution outside the training window, right? If we do that, then everything that happens outside the training, it's acceleration, right? So we try that. We try it with different Reynolds numbers, etc. in the paper. And in this particular case I'm showing you, we have a high order polynomial 8, which will only be run for the training window, okay? And then we have a low order polynomial 3 that we will correct with our neural network. So in this case, which is conservative, we have a ratio of time steps for advancing of 3. So P8 is 3 times lower than P3. So these are the results. What we get is when we compare the high order solution to the low order solution without any corrections, we see this type of behavior, right? So there's no corrections, there's no neural network whatsoever here. This is the error that we get. Now, if we include our neural network in the low order solution and we compare the results, and we only train for a limited time frame, this one, here we are correcting, and then we let it keep correcting the neural network, but without training. So the P8 solution is only needed in this part. What we see is that we have decreased the error, right? We have decreased the error for a long time after the training. And this, of course, all this region is acceleration because we don't need the P8 solution. Right, so what we see is overall, in this particular case, we get 12 times faster solutions than the p8 solution. Oh, but there is an elephant in the room. Okay, so if we were getting the p8 solution, if we were recovering, so this is correcting our p3 solution, but it's not correcting it to be a p8 solution. If we were correcting it to be p8, we will have a line of error here, down here, because we are correcting everything. So the elephant in the room is we are correcting it, we're getting a more accurate solution, but what's the order of this solution? Right, so to check this, in this particular case, we have run a bunch of polynomial orders, right? And we are comparing the solution, the errors when we do the purple one, which is with the neural network. And what we see is that we are getting more or less polynomial orders 5 or 6, right? So the accuracy is 5 or 6, such that if we compare the cost of using P3 neural network and we compare it to the P6 cost, the advantage, the accelerations that we get is 4 or 5 times faster, right? So it's not the 12 times that we had before. Actually, we are 4 or 5 times faster, but there is accelerations. So I think with this, I will conclude. I have an additional slide on reinforcement learning, but I think I'm going to skip that. Right, so overall, we have a horses 3D is available on request. This is an old slide. It's on GitHub, right? So you can go and download it if you want. It shows exponential decrease of the error, whilst we only have a linear increase in costs. So it's advantageous to use high-order polynomials. We have a bunch of multiphysics implemented. And we are working on acceleration techniques based on neural networks and this kind of stuff. So with this, I think I'll conclude the talk. Thank you very much.
So thank you, Esteban, for this very comprehensive overview of the code you are developing. So I would say let's open the stage for questions. Just to the participants, just feel free to unmute your mic and ask a question. Go ahead, Marcello.
Thank you, Francesco. Here's Marcello Meldi from LMFL. Thank you very much, Esteban, for the talk. Very interesting and very complete. I actually have one question and potentially a second one. The first one is about the discussion of the usage of machine learning to improve the polynomial order of your solution. The very last thing that you presented. There's one thing that I didn't understand during the training phase. Was it a training phase that you performed online and with the streaming data, or did you have to perform the training of the neural network offline, and so you have to run the simulation twice in the phase, in the window in which you perform the training?
Right. So in fact, in this paper, it's the conceptual idea that we wanted to put forward, check the errors, etc. We haven't gone the step further that you're asking for in how we can do that efficiently. So in this particular case, we run the P8 for the whole cycle, we run the P3 for the whole cycle, and then we checked, right? So we haven't done that in a proper implemented way, if you want. This is, of course, the next step. In fact, there's a few things that we need to work on, and it's, for example, so I don't know how I can read that. Yeah, so for example, another thing we haven't considered fully is that, okay, you train for a while, then the error keeps increasing, right? Keeps increasing. And after some time, what you want to do is you want to take this corrected simulation and run P8. So using at the starting initial state to run the P8 for a while and perform another training, right? So that will bring the curves down, and then they will start again. So, and this, we think that can be automatized some way, in some ways. We have some estimates on how the error increases, etc. That can help to know how these things are increasing. So again, in the implementation side, I think there's a few things to look at, in particular what you are mentioning. So do we do, the training as we go along or not? In this work, we have done it offline because everything happens, let's say, offline.
Okay, thank you very much. And Francesco, may I ask a second question?
Yeah, please go ahead.
Okay, thank you very much. It's about the IBM. When we talk about the traditional solvers formulated with finite volumes or finite difference approaches, we know that it is extremely difficult to get an order, more than an order 2 quality in terms of mesh refinement. When we refine, we do not have something that scales better of order 2, so it is kind of difficult to exploit high order methods, in particular with finite difference. And did you perform an analysis of mesh convergence for the IBM similar to the one that you presented at the very beginning in terms of H and P variations?
Yes. So what happens when you're using merge boundary methods is that you have two types of errors. So one is related to the discretization, and this one we can bring down by using a high polynomial order, so there's no problem there. And then there is another error that arises from not having smooth gradients at the boundary. So we have checked that. So if you place smooth, gradients at the boundaries, you're only left with the error in the discretization, and then you get very high order convergence. Right, so this you can check in this page, in the first one here, down here. But this is when you, for example, impose the gradient, or the gradient of your solution inside the immerse boundary. If we get rid of that, it's true that this factor, this not having the gradients, limits the convergence. But this limit of convergence is very close to the walls. So overall, the flow field. So if you're checking, for example, the vortex shedding away from the airfoils, what you get, you see convergence. You see convergence in terms of polynomial. So you're not downgrading the overall solution. You're very locally downgrading the solution near the boundaries if you're not imposing the gradient right. There are some people in developing fake gradient solutions inside the bodies to avoid this type of second error, and then allowing higher order solutions there. So there are ways of bypassing these limitations.
Okay, thank you very much for your answer and for this very nice talk.
Thank you.
Actually, I have a question related somehow to also to the interface, which is considered when you presented the multiphase flow. You said that locally you increase the accuracy of the polynomial when you deal with the interface, right?
Mm-hmm. In the multiphase one, yes.
Yeah, and so do you see any effect on sort of production of satellite bubbles or satellite droplets, or which are known to be somehow produced by, for example, VOF methods? Do you have similar things, or does it improve the solution in comparison with experiments in that case, or?
Okay, I think there's more than one question there. So I don't think we see any spurious physics coming out from the interface resolution. It's true that canhillier is a bit tricky because you have a few parameters that you have to play around, and these parameters can change the physics. But once these ones are set, we don't see changes when we increase the discretization. Sorry, what was the second one?
Yeah, I mean, how does it compare with experiments in test cases, which are typically producing like spurious droplets or?
So we've checked with typical, well-known cases, and everything looks quite okay. We don't see any particular. I think at volume of fluid it's a bit more tricky because you have to do a lot of corrections, no? So the basic method is very easy to understand, but then you have to do a lot of corrections to get things right. Here, the only thing you have to worry about is to solve this additional equation okay, right? And let me know that it's not an easy equation to solve, because you have here a second order derivative and here another second order derivative. This guy goes here and you get a fourth order derivative.
Yes.
So this is very stiff, right? And it's not easy to solve. So, but we managed to solve it. But if you are careful with solving this equation, I think then you're fine.
Yeah, actually, one more point about this equation. It is the problem, the usual problems reported for the phase field is that it's not very conservative in terms of right, in terms of mass conservation, and that's reported also for pure spectral methods that use very high order. Do you experience an improvement? Because I think that the strength of your method is that you can locally refine tracing the interface, which would be quite an advantage with respect to.
So I think you're pointing to an interesting question, but I think it's related to the continuous Galerkin. So the high order method, when you use a continuous setting. So in the continuous setting, so you can think in terms of finite elements, the continuity so there's no guarantee that you have local conservation. The conservation is global in the whole domain. But in DG, because you are discretizing at a local level and then using fluxes to transmit the information from one to the other, you're guaranteeing that you have local conservativeness in each element.
Yes.
And for this reason, I think we don't encounter these kind of problems that you're pointing to.
Okay. Yeah, that's true. I missed this point. Actually, DG is basically high order finite volumes.
Exactly.
That's because you impose fluxes. Okay, yeah.
Yeah,
okay.
but
very interesting.
You ensure local conservation. So this is a nice thing for DG.
Very interesting. Very interesting. Thank you. Let's see if there is someone else who would like to ask a question. Just once again, feel free to unmute your mic. Go ahead, Hannah.
Hi, thank you. Very interesting discussion on this last point. A problem that I've understood is difficult with the conventional methods is when you have a phase interface with a high density contrast, and say it's a liquid gas system, and you want to also have a density variation in the gas phase. And that's much more difficult than if each individual phase is constant density. Does this method address that regime?
We haven't tried that. To be honest, we haven't tried that. We have some. So this particular work we did with an incompressible solver. Right, we were copying the incompressible Laskowski to these Canhillier equations. Can be done also with a compressible version, but we haven't done it.
Yeah, because I see you had the word compressive down there on your slide, down at the bottom.
Where, sorry?
On the slide you're showing right now, it said compressive down under VOF. I guess that's future work.
No, but sorry, but this is from a paper. So this is just to see the overview of all the types of methods.
Oh, okay. So it's not necessarily within your.
No. Of course, this is all classes of VOF multiphase type of methods, and we are focusing only on this one.
Okay.
Yeah. Sorry for the confusion. So this is not. It's not even our paper. So.
Oh, okay. Thank you.
It's a summary of methods.
Right.
But anyhow, you can use Canhillier with compressible or incompressible solvers. In this particular thing, we were using incompressible, and to do the incompressible, we were using compressibility correction, artificial compressibility approach, and this one limits you in terms of how you're treating the density changes and the ratio of densities. So we were a bit cautious and we didn't push that a lot. So I think if we want to consider what you're mentioning, we have to revisit how we do the incompressible part as well. So not because of the Canhillier, but just because of the incompressibility way we advance.
Because that would be interesting, because as far as I know, that the regime I described, there's not really any good method right now. I'm not
Okay.
100% sure about that, but that's my impression.
I don't know. I don't want to say we can do it.
Yeah.
We can think about it. Let's put it this way.
Yeah, that's all I'm suggesting.
Yeah, no, it seems interesting.
Yeah. Thank you.
Thank you.
Well, thank you. So let's see if there is someone else who would like to ask a question. Once again, just feel free to unmute your mic, or you can write in the discussion in the chat and I can report it.
Sure. You can always write me an email afterwards as well if you have more doubts.
Let's see once again. So maybe I do have a last question if I can ask. So you mentioned that you use artificial viscosity for imposing for imposing the incompressible constraint. So is it like in just in connection with the question of before, like is there a way to turn this method into a kind of a all-math approach or something like that, in which you have an incompressible viscosity just in one phase and you relax it down, or are you aware of any of these approaches, or not really? Because I think the tricky thing is that at the interface, technically that's the most intricate part to deal with, right?
Yeah,
the equation of state changes.
yes, I'm not sure. We haven't looked into that.
Okay.
With detail.
Okay, because it seems quite a potential. It seems to have great potential, actually.
Yeah, I mean, what we do know is that when you have large radius of density, this artificial compressibility is not very well suited, and then we need to, or we should go to a fully incompressible solver. Like all the work on sliding meshes work with a really incompressible solver.
Mm-hmm.
So we know how to do it. Only in this last version we don't have it implemented yet. So this is a way to solve these very large ranges of density. So this is easy to solve.
Mm-hmm.
Now, if it wants, so I think, if I'm not misunderstanding, what you want is one phase to be incompressible and the other one to be compressible or something.
Yeah,
like
basically, yes.
So that's basically what you want, and I'm not sure how easy it is to do.
Yeah, that's.
I think that's tricky, of course. I'm not saying it's impossible, but I'm not. I don't know what happens.
Okay.
Interesting, nonetheless. Really.
Yes, that's okay. Thank you. So then I think we can. Sorry. Sorry. Then I thank you very much for the talk of today, for replying to so many questions. It was very interesting.
Thank you very much.
It's also very important for the community that the code is shared on GitHub, so that can be, I hope, a good advertisement for the code. And thanks for the very clear and detailed talk. Thanks.
Yeah, thank you very much, Francesco. And well, I'm open to emails, collaborations, etc. So just let me know.
Okay. Thank you.
Thank you again.
So I invite the audience to thank our speaker, and I wish you a good evening.
Thank you. Likewise.
Bye.
Bye.